get my mic up. So yeah, we've handed back printouts. I still have a few things I want to go over with you. And specifically, the participation data is updated as of last Thursday. So that's October 26th. You'll see again two different lines in the grades page. One says clicking answers as of 10/26, and one says clicking correct as of 10/26. All right, now the morning section has 23 official questions, and this section has 24. All right, so we're a little bit different from the morning class for now. Eventually we'll get them evened out. So to get your participation, you might as well jot this down in your notes so that you can get your grades calculated whenever you feel like it. Okay, so the first thing you have to do is calculate your participation percentage. So however many you've answered, and that's however many correct or incorrect, divide that by 24. So some number n divided by 24. And then you put that into the proportion. Now the proportion is still the same. It's your percentage divided by 0.85 on one side, and then on the right side, your pointage divided by 45. Now that's the same one that's in the syllabus, and we've actually talked about it a time or two since then. All right, and we're going to do an example of that, or you're going to do an example of it in just a few minutes. Now, homework pointage I want to review with you. We haven't done this yet, I don't think. It's just a straight percentage. Now, right now we have, as of 1:30, when the last assignment closed, there's 25 points possible on the 4 or 5 homeworks that we've had. Now, don't include homework 0, because that was just an attendance. Are you supposed to be scary? Oh, okay. That's just your normal outfit? Oh, sorry. Yeah, oh. Okay, just checking. I saw one guy this morning. Boy, did he look really good. There's been some good guys, some good costumes. So anyways, out of 25. So, and don't include homework 0. And then just multiply your percentage by 10 and then round up. So for instance, if you have 21 out of 25, all right, that's 84%, 0.84, okay? And so then multiply that by 10, so 0.84 times 10, that's 8.4, all right? Now technically that's your pointage, but I always round it up, so you would actually have 9 out of 10, all right? Now we're going to do a calculation on your iClicker, so get your iClicker out, get your calculator out too, if you feel like it. Madison. See, I learned your name. And Talia. Get your clicker ready. If you have your clicker. What's that? No, it won't work that far. Yes. It's got a good reach. It's a little cell phone, but it's not that good. All right, so anyway, so remember, I always round up just to give you guys the benefit of the doubt and cut down on whining for students. I shouldn't say that, but sometimes you guys are all nice guys. You're all very nice young men and young women, and I'm sure you'll never whine about your grades, but in past semesters, there's been a little bit of whining. So anyways, let's try some clicking now. So for instance, your clicking answers as of 10/26 is 15 out of 24. Go ahead and click calculate the participation pointage. And let me start the question. Okay, you're on frequency DD. And we got a multiple choice going. and do your calculation. And, definitely coordinate with your neighbor. Now it's okay to talk with your neighbor. So yeah, double check and just kind of calculate. And you guys, we're going to go through it step by step in case you do get tripped up, but see what you can do. Basically, you just got to solve that proportion. Okay, 45 seconds. Abby, did Courtney tell you about your... Yeah, you messed up your PID. You forgot to fill in your PID in the test form. You got to, on your Scantron. So you got a grade, and I'll be posting them this afternoon, but you're not going to have a printout. So, but if you come during office hours, you can review your test and figure out which questions you got wrong. Okay, so remember that you got to type in, you got to bubble in test form A, B, C, or D, and then your PID as well, where it says ID. Okay, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And I can tell you that we got a little bit of splaining to do because look at this, a little bit of spread in the answers. So that what that means, it tells me that you as a class, as a whole, are, I don't know, kind of flailing a little bit. So let me see if I can move this out of the way here. All right, so let's go back to the podcast and let's take a look step by step. So if you didn't get the right answer, and oh, by the way, the right answer is 34, this is where you start. So your percentage, 15 out of 24, is 62.5. So you go 0.625 divided by 0.85. And then the rest of the proportion, that's the same. That's always going to be the same. The right-hand side is always going to be your points divided by 45. So what I normally do is calculate the quotient on the left first. Okay, so in that case, it's 0.7353, right? And then, and now the right-hand side is, I haven't done anything with the right-hand side, still x over 45, and x is your pointage. And now we want to cross multiply and get 45 to the other side, okay? And that tells me, all right, I've got to multiply 0.7353 by 45. And when you do that, you get 33.0885. And as always, you round up. So don't forget to round up at the very end. And I'll be, you don't have to worry about it because I'll be doing it at the end of the semester when I officially crank out your grades. But if you don't, like this week, you're trying to figure out what your grade is as of today, as if this were the end of the semester, you want to remember to round up. Okay? Now let's do another calculation. Your homework performance is 16 out of 25 so far. you're a little bit stinky on homework. Let's figure out what your pointage is. All right, so let's do another question. Let me start it. And I'll give you a minute for this. This one's a little cinchier. But we'll go step by step through this one, and then you'll know how to put together all the stuff for your grade. Thirty seconds. $15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Yeah, we got another, we got a little explaining to do here too. Let's go through it step by step. 16 out of 25 is 0.64, 64%. And then multiply that by 10, that's 6.4. All right. Now, you always round that up to 7, to the next higher number. And look, you know, if you were in math class and you were trying to round off a number, that one would round off to 6. But for me, when I'm giving you guys your grades, I always give you the benefit of the doubt.
Unknown caller.
The one place where I give you guys the benefit of the doubt is on this, and class participation. All right, so that's how that works. All right, now I want to also mention to you the exam 3 clicking numbers are not up yet. They will be hopefully this week. Might even do them tonight. And I've had a lot of other things on my plate. Also, remember that the Scantron grade that you have now, plus whatever you get from clicking, add up to your total score. So what you have in your printout is not your total exam grade, unless you get 0 on the clicking, of course. Hopefully, so everybody got some points. By the way, I want to make this last comment concerning participation points. 45 points out of your 260 for the semester comes from participation. And it requires that you answer, whether correctly or incorrectly, 85% of all the questions. Now, right now, the number of questions is kind of pokey. It's only 24. But we're going to keep building up the number of questions, and we'll have quite a few by the end of the semester. If you get 85% of them answered, whether correctly or incorrectly, you'll get 45 out of 45. And I'm very happy to say that right now, the number of students that have 45 out of 45 as of today is 41% of class. Now, it's not a majority, but it's getting up there. And by the end of the semester, I'm hoping that all of you will have 45 or 44 out of 45. It is a nice chunk of change, and it's almost as big as a midterm. The midterms are 50. All right, so this one, usually I make it so that the midterm and the homework, and actually the homework and the clicking together add up to 55, so that's actually bigger than a midterm. I usually make homework and clicking add up to the same as one midterm. And the reason I do that is so that it gives you a little bit of extra horsepower in your grade that comes in at the end of the semester, after all 3 exams are on and after all the clicking is done. At the end of November, you'll know what part of 45 out of 45 you've got. and for many of you, it will be 45 out of 45. So, and just to remind you, when you're doing here's a diagram of the scantron. So no matter what you're doing, when you're filling out your scantron, you want to fill out this part here. Some 800 numbers calling me. Remember, Abby and the rest of you, you got to fill in test form. Some of you didn't get printouts. You got to fill in the test form up here, A, B, C, or D. And then up here in this area, you have to fill in your UCF ID number. Now, you don't have to write the letter anymore. You used to. But now just the 7 numbers is sufficient. All right. Now, any questions about this and that before we go on to astronomy and stuff? Yes, Desiree.
Is cumulative, or is it just going to be like all the sets?
Question is the final cumulative? The answer, yes. And all right, let's go back to the sun, and let's just do a quick recap from last time. We talked about energy in general. I gave you several examples, including a Bumblebee Camaro doing the quarter mile, 115 miles per hour in 12 seconds, developed 2.2 megajoules of kinetic energy, and that corresponds to an average power of 176 kilowatts. And we compared that to a hairdryer, 176 or 1.76 kilowatts. We also talked about the energy usage rate. A watt is basically 1 joule per second. And we rate the luminosity of stars in watts, or we can measure it in watts. Or we can compare it to the sun, a multiple of, twice as luminous as the sun, 0.8 times as luminous as the sun, stuff like that. But watts is definitely one of the luminosity measures. Another thing we work through is rest energy. I'm going to give you a little more instruction about that in lecture today, just a minute. Rest energy equals mc squared, the famous equation. And what we did was figure out how much mass of the sun's 10 to the 30 kilograms goes into its luminosity per second. And we also figured out how much per year. And, we figured out that it's a pretty small fraction of the sun's mass on a second basis. It's about 2 parts per sextillion. 2 parts for every 10 to the 21. So 2 kilograms for every 10 to the 21 kilograms of the sun's mass. Somebody's messing around with me here on my phone. I'm going to turn this thing off. Hold on a second, you guys. Okay. Another thing that we talked about last time was the Kelvin scale. And I'm going to give you a clicker question on this in just a minute. Remember, this is the metric scale that we use for thermodynamics. Basically, it's a scale where every temperature is positive. And it's based on our idea of the kinetic theory of gases, in which the temperature is a function of the average kinetic energy of the particles in a gas. And kinetic energy, 1/2 mv squared, is always positive. So the average kinetic energy of the particles in a gas, like the oxygen molecules, CO2 molecules, all that works together for the average temperature, or for the temperature and the average kinetic energy. The average kinetic energy will also always be positive. So you want, if you're trying to work with individual molecules and figure out exactly what's happening with all those molecules, you want a positive scale for temperature, and the Kelvin scale does that. We talked about Roy G. Biv concepts: red, orange, yellow, green, blue, indigo, and violet. And we're going to talk about that in detail today when we talk about Doppler shift. But before we do that, let me do one more clicking question with you. A simple calculation, just to get your brain cooking again. And this is from Celsius to Kelvin. And you can actually use this diagram to figure it out. Okay, the human body temperature is 37 degrees Celsius. How many kelvins is that? Can you tile that so that I can see the timer? No. Yeah. That's good enough for now. "40 seconds. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Answer is B, and the way that you figure it out is just adding 273. So you can kind of see that here on this table. From Celsius 0 to Kelvin, freezing water, 273. So 0 plus 273 equals 273. And down at the bottom of the scale, and actually everywhere on the scale, it's always from left to right, add 273. So that's the answer for this one. Another thing I want to make a note of to you, we kind of alluded to it already. Every physical object in the universe will have a temperature, and it will be a positive number on the Kelvin scale. And so that allows you to eliminate A and C. So then you just got to figure out between B and D.
You can also eliminate TB, because it's under 0 Celsius.
That's right. So if right, it's under 0 Celsius. So
There's no calculation.
yeah, so it's, if you do a little bit of exercising of your coconut talia, then good. Don't fall asleep in class. Because if you do, you'll lose all my handy tips on how to crush my exams. All right, so anyways, that's the Kelvin temperature. Now, I want to reinforce the E equals mc squared, matter into energy, energy into matter idea. And, everybody, what we did last time was we talked about the fusion reaction where just a teeny little bit of mass is lost in the reaction, and we know that mass that's lost is converted into joules of energy, and it's actually a lot of joules of energy. If you lose 1 gram of mass of anything, that is equivalent to 90 trillion joules. And that, my wonderful students, is a lot of joules. It's a lot of energy. And to show you, I'm going to compare this gram for gram, joule for joule, to one of our biggest energy sources in the USA, and that's the Grand Coulee Hydroelectric Dam out in Washington State. Now, the rated power of Grand Coulee Dam, if all the turbines are cooking, is 6.8 gigawatts. And so that's good for at least 5 or so flux capacitors. And if you ran Grand Coulee Dam at 6.8 gigawatts and converted all that energy into mass, converted it all into water, And if you ran it from, for a day, a month, a year, and in fact, if you ran it for the entire age of the universe, in other words, if for every instant of time from the Big Bang up to today, which is about 13.8 billion years, if you ran Grand Coulee Dam, how much water would that convert to? So you might think, well, that would fill the universe with water. That'd be a lot of water. It'd be, zillions of grams. Wrong. It would basically be about 157th of the water in Lake Okeechobee. So the biggest power source that we have in the United States, or one of the biggest, running for the longest time interval, if we could imagine converting all that energy into matter, it would just fill this lake by 157th. So it's just a little skim of water in Lake Okeechobee. And if it were a smaller lake, it would fill it up. But, Lake Okeechobee is pretty big, okay? And it's not that deep, but this tells you. So write down that fraction. Grand Coulee Dam, age of the universe, full power, converting all to water, 157th of Lake Okeechobee. In other words, Jack. The amount of energy, gram for gram, is enormous. Ginormulous. And so the biggest thing, or one of the biggest things we got, I think the Russians have got a bigger one in Siberia, and I think they got a bigger one in China now. 3 Gorges, or whatever it's called, 9 Gorges Dam. But this, Grand Coulee is pretty big too. And the biggest thing we got, this is all it makes. It's amazing. And that is why a very small amount, basically in an atomic weapon, you take, look at my hands up here. Look at this. See this? See my hands? You take about this much uranium and you destroy a city. It's just, it's hard to imagine. And most of that uranium is not even used. Just a small fraction of it's converted into energy. So it's amazing if you think about it. But it all goes back to E equals mc squared. Now, I want to talk more about Doppler shifts. We've already looked at the Doppler shift for sound. We looked at YouTube or the freight train. Now, a couple things about this I want to point out to you. And that is, if you were at rest in the switch yard and you got the engineer, you go like this, and the engineer blows the horn, it'll come out at a certain note. Now, if the train starts moving, and by the way, for sound waves, the pitch of the sound waves corresponds to the frequency of the sound wave. Okay, so the A above middle C is 440 cycles per second. So what that means is 440 pressure waves hit your eardrum every second. A little bit of high pressure, a little bit of low pressure, high pressure, low pressure, high, low, high, low, high, low, 440 times per second, and that'll sound like the A above middle C. Now, the fancy metric term for cycles per second is the hertz, Hz. Okay? So 440, and we're not going to work too much with that nomenclature stuff, but that is how we would talk about the frequency in terms of hertz. So if you're at rest in the switch yard, you hear the standard value of the pitch. Now, if the train is coming toward you, you hear a higher pitch. So when we were looking at that YouTube, we were actually listening to the higher pitch because the train was coming toward the cameraman. Right? Similarly, once it passes the cameraman, now it's moving away from him, and that's when we heard the pitch go down by a note or two. All right, now that's with sound waves. And with electromagnetic waves, it's very similar. Although the electromagnetic field is definitely not the same as the sound wave system. If the source of electromagnetic radiation is moving away from the observer, the frequency decreases, just like in the train. Once it passes that guy, the pitch goes down. Same thing with electromagnetic radiation. Now, we don't hear that as a pitch, but we see it as a color. The wavelength increases. When the frequencies get smaller, the wavelength gets proportionally bigger. All right? Or I should say inverse proportionally bigger. What we would say is, we wouldn't say that the pitch goes down or the pitch goes up or anything like that. What we'd say is that the light, the radiation reddens, or we would say that it has a red shift. Right? And that means that the wavelength is shifted towards the red end, the R end of Roy G. Biv, by some amount. And the faster you go, the bigger the shift. And by the way, students, if you watch the World Series, or if you drive around Orlando, now nobody in here, I'm sure, is an unsafe driver. You're all good citizens, I know, and you never get tickets of any kind. But you know that people do get speeding tickets, and it's because of the Doppler shift. You know, the radar gun that the police uses, same as, in a baseball game. They put a radar gun on the pitcher, and they measure the speed of his fastball. Yeah, you can actually measure the Doppler shift, the red shift, or actually it'd be a blue shift because the baseball's coming towards the observer. But the police officer can get you either coming or going. He'll get a red shift if you're if you're moving away from him, or a blue shift, and that's what we got here in B. He'll get a blue shift, the radar will bounce off your car, and blue shift. So the observer measures a larger frequency, that means a smaller wavelength, and we would call that a blue shift. And that we use the same word, blue shift and red shift, whether we're talking about X-rays, which are neither red nor blue, but we say that it's a blue shift or a red shift. Red shift if the wavelength increases, blue shift if the wavelength gets smaller. We use it for ultraviolet. We use it for infrared. We use it for radar, radio frequency. We use it for everything. Red shift and blue shift. It's just our physics terminology. All right, now in the lab, the H alpha, go ahead and write this one down. We'll probably talk about H alpha a lot in the next month. H alpha in the lab, when you're at rest with respect to the source, it is 656 nanometers. Now, a nanometer is 1 times 10 to the minus 9, a billionth with a B, a billionth of a meter. All right, and the wavelength for H alpha that we saw on the first day of class is 656 nanometers. Now, if the source is moving away from you, you might measure the wavelength at 658. It might not be a big shift. Okay, that's just a couple nanometers. But we can measure that. It's not that hard. Measure a red shift of that size. If it's moving toward you, it might come in at 653. That's not a ginormous red shift. But, we can measure that, okay? And when you measure it, if you know it's H alpha, then also this, using this fancy physics formula from relativity, you could figure out the speed of your source. So if you're looking at a car out on the highway, if you're a policeman, if you're looking at a baseball coming towards home plate, if you're looking at a star, if you're looking at a part of a star. If you're looking at the left side of a planet that's spinning, and the left side and the right side of the planet that's spinning, you'll be able to tell that it's actually spinning. Because one side will be red shifted, the other side will be blue shifted. if it's spinning in your plane of motion. Now, side note, technically 658 and 653 that I just gave you as examples, those are still in the R region of Roy G. Biv. All right, so you would say that 658, it's still red, but it's a little bit redder than standard H alpha in the lab. Right, so you would say it's shifted a little bit deeper into the reds. And you can get it shifted out of the reds completely. Once you get above 700 nanometers, you're out of the reds and into the infrared. Right, so we see stuff that shifts H alpha into the infrared. It's not that common, but we can see it. Similarly, 653, that's still red too, but it's shifted toward the B, the blue part of Roy G. Biv, so we call it a blue shift. All right, it's still, even though it's still red. So it's a little bit, so an astronomer or a physicist would say, yeah, that's a little bit bluer than usual, even though it's still red. And even though you wouldn't be, visually, you wouldn't be able to tell it apart, but if you were in the lab and you were, able to measure it and stuff, do a little trig and stuff like that, use your protractor and whatnot, yeah, you'd be able to measure that and you'd say, oh yeah, we got a little blue shift going on here. So the upshot of the red shift idea, the Doppler shift idea is, if we have a known source, if we know something's got all the lines of hydrogen, H alpha, H beta, H gamma, H delta, and so on, or if we know that if we're looking at helium, and helium can show some red shifts and some blue shifts as well. If we see a blue shift or a red shift, it tells us the state of motion of the object that we're looking at. Now, here's an example. Yeah, the sun. This is figure 15, or figure 4 from chapter 15. And yes, this little dot here is the Earth compared to the sun to scale. It's amazingly small. That's our big, gigantic planet. And compared to the SUN, it's a blip. Now, here is what we call a Dopplergram. Okay, go ahead and make a note of that word, Dopplergram. And this one is from the SOHO spacecraft, looking at the SUN. You can see some sunspots. So actually, this here, I think, is, they caught the space station. This is the space station going across the sun. I'm not sure. But here's the key down here. Black is -2 kilometers per second. White is +2 kilometers per second. So what that means is +2 kilometers per second is going away from you. I think that means away from you. And minus means the opposite, towards you. So what that tells you is the right side is going away from you and the left side is coming towards you. So that means it's spinning. Let me repeat that. Opposite Doppler shifts on either side tell you the sense, if you think about it, that it's spinning. And this is one way we can verify something that Galileo deduced from sunspots. Galileo said, the sun is spinning. Because he could see the sunspots moving from place to place. And this also helps us verify what Galileo figured out. And this is much more precise. So, and we do this for planets. We do this for cars out on the highway when they're trying to nab speeders. Then we do this for, what we do this for? We do it for atoms. We can use it in the atomic physics lab. We can actually measure Doppler shift for groups of atoms. So it's amazing. Here's another application. This is a close-up view of the surface of the SUN. This is I forgot to put it in. This is figure 5 from chapter 15. And this is a close-up view of what we would call the granularity of the surface of the SUN. All right? And we know, go ahead and make a note, granularity of the sun, chapter 15. And the granularity of the sun, we know, is a result of convection. So all these are little convection cells that rise to the photosphere of the SUN. And how do we know that they're convecting? Because we can look at the left side, the right side, the middle, top, bottom, and check the bigger ones anyways, and we can see that there is Doppler shifting. It's rising in the middle, and it's descending. It's going away from us around the edges. So where it's dark, that's where it's descending. So we know that that stuff's cooler. Stuff that's cool and descending is that's a convection cell. It's like gigantic, like here on Earth, convection cells, you can see them in the kitchen, but you can see them outside every day, every time there's a thunderstorm. Hurricane is a gigantic convection system. All right. Now, the cool thing about these convection cells, and here's a pull quote from chapter 15. This structure of the photosphere is called granulation. Granules, which are typically 700 to 1,000 kilometers in diameter. Yeah, that's about the size of Texas. So it's and some of them are bigger than that. Some of them are, the really big ones can be the size of the Earth. So it's amazing. And so what we're looking at here is the convection cells at the very top of the convection zone in the sun. So there's the photosphere, and right below that is the convection zone, and then right below that is the radiation zone, and then right below the radiation zone is the core where the nuclear reactions are taking place. So you can think of these as like weather systems here on Earth. They're pretty much disorganized, unlike the convection cells that form a hurricane. That's basically a highly organized convection system, lots of cells, all organized. But this one's not really that organized usually, but they're ginormous. They're really, really big. Another thing about the photosphere is you might think, oh man, it's ultra hot. Students, the temperature of the photosphere, 5,800 Kelvin. Students, the temperature of the photosphere, 5,800 Kelvin. My wonderful students, the temperature of the photosphere, 5,800 Kelvin. You got it? Okay, 5,800 Kelvin. Because we're going to when we're looking at all the stars in the galaxy and trying to see patterns and stuff, that's one of the things we're going to check, the surface temperature. All right? And we're going to compare it to the SUN. We're going to compare the color to the SUN. We're going to compare the mass to the SUN. Because the sun is the closest star to us. So it makes sense to look at it. So you might think to yourself, okay, the surface of the sun, boiling hot, ultra high pressure, dense, like the core of the sun, but it's not really. It's less than 10% of the Earth's atmospheric pressure at sea level. All right? And the density is about 1/10,000th of Earth's atmospheric density at sea level. But it's bright, it's incandescent, delivers a lot of luminosity, and it's convecting. It's a pretty complicated system, you think about it. So here's my final quote for today, and we'll dismiss in just a few minutes. The solar photosphere, where the density of the atoms is sufficiently low, and the photons can start to escape from the sun. Before that, when you're down here in the convection zone, and especially down here in the radiation zone, it takes thousands of years for a photon of light to start in a nuclear reaction in the core and make its way all the way to the photosphere because it gets bumped around. It hits nuclei and electrons, and every time it does, it changes direction and loses a little bit of energy. And eventually, by the time it gets out to the photosphere, the density is low enough, one last bump, and away he goes. The next stop, planet Earth. All right, let's dismiss early. Finish the readings, and I'll see you on Thursday. If you didn't get your printout, come on up. We'll catch you right now. Okay.
Okay, what were the correct answers?
Hold on a second. Let me get my cursor. Here we go.